Let us talk about how multi-frequency continuous wave radar can be used to get range information of a target. So first, we need to understand that in case of unambiguous range for CW radars, only simple continuous wave radars, single frequency continuous wave radars, that is lambda naught by 2 only, which is very small, almost impractically small. So this is the reason we need to move to other technologies, one being this MFCW, and the other being the FMCW. We are not talking about FMCW in this one. We are talking about how MFCW can be used to increase the unambiguous range. So let us consider first with the transmitted signal. Let us express the transmitted signal. There are two transmitted signals in case of multi-frequency radar. One, say we are using two frequency continuous wave radar. In that case, we have two frequencies, F1 and F2, and in that case, we shall have we can express two transmitted signals. One being V1 txt equals to sine 2 pi f0 t plus phi 1, and the other being V2 txt equals to sine 2 pi f0 f2 t plus phi 2. Phi 1 and phi 2 being the constant phases of the respective signals. So the received echo. Now we can express the received echo of these V1 tx and V2 tx respectively as V1 rx and V2 rx. So what is the expression? Expression is sine 2 pi f1 plus minus fd1 into t minus 2 pi f1 capital T plus phi 1. So this is coming from for this one, and for V2 dx it is this one. It is similar in nature. So in here our fd1 is the Doppler frequency, fd2 is the Doppler frequency. Fd1 is the Doppler frequency associated with the frequency f1, and fd2 is the Doppler frequency associated with the frequency f2. And this t value is the time taken by the signal to travel from the transmitter to target back to the receiver. So there is a time. If our distance between the transmitter receiver and the target is r, then this t value is 4 pi f1 r by c. Let us say that again. So if our tx and rx are at a distance r from our target t, then t value, there is a time taken. This is the target. Okay, this is t for time. So t time taken is equals to twice r by c. So if we replace that, this will become 4 pi fr by c. We should, okay. So come again. Let's say t equals to twice r by c. So our 2 pi ft terms will become 4 pi fr by c. So if we rewrite this v1 rx signal again, so this becomes twice pi f1 t sine of twice pi f1 t plus minus 2 pi ft1 t minus 4 pi f1 r by c plus phi 1. Now phase difference between this v1 rx t and v2 and v1 txt, these two, there is a transmitter in between. The transmitted and received signal at a singular moment would be del phi 1. Let us express as del phi 1 would be 2 pi fd1 t minus 4 pi f1 r by c, because all other parts are common. So this becomes our phase difference as written here. So Similarly, we can derive the phase difference between V2TXT and V2RXT, and that will be our plus minus 2 pi FD2T minus 4 pi F2R by C. But we can express this FD1 and FD2, they are almost same in value, so we can express this as FD. Okay, let us see how these two are same. Let us start with the expression of FD1 and FD2. So this is twice VR by lambda. From that formula we are getting FD1 equals to twice VR by lambda 1 and FD2 equals to twice VR by lambda 2. Thus we can express it in terms of frequency as twice VR by F1 by C, and in this case twice VR F2 by C. So if we divide FD2 by FD1, it will become F2 by F1. So in case we express F1 as F and F2 as F plus delta F, where F2 minus F1 is delta F, then FD2 by FD1 can be expressed as F plus delta F by F, which equals 1 plus delta F by F. But delta F is very small. If delta F is very small, these terms become 0. So almost equal to 0. So in that case, FD2 by FD1 equals to 1, or FD2 equals to FD1, which we are expressing as FD, simply as the Doppler frequency, common Doppler frequency FD. So our previous these two expressions, del phi 1 and del phi 2, now becomes this del phi 1 del phi 2, where our FD1 and FD2 terms are replaced by FD terms. Now for del phi 1 it will become plus minus 2 pi FD2 minus 4 pi F1 R by C. For delta phi 2 plus minus 2 pi FDT minus 4 pi F2 R by C. So if we do the phase difference in these two phase values, and we this FDT terms are cancelled, and we are left with only this F2 minus F1 term, which is nothing but 4 pi delta FR by C. So our phase difference is directly related to the frequency difference of the two frequencies used. Now for RM, if we can, and in this expression we are already getting the range value R. Now for unambiguous range detection, if del phi 1 minus del phi 2 is less than equal to 2 pi, we can see that then we can have an unambiguous phase value, and that will lead to an unambiguous range. Now at del phi 1 minus del phi 2 equals to 2 pi, there is a maximum limit of this unambiguous value. The maximum unambiguous range would be would be R unambiguous is to C by twice delta F. Thus we can see now that this unambiguous range depends only on delta F, that is the difference of frequency of the two values used, but two frequency values used, but not on individual frequency. Now let us take an example. So for 10 km unambiguous range, what will be the delta F required? So if we compute, we can find that it will be only 15 kHz. And also if our delta F value is lower, as we lower, our range unambiguous can increase. We can go, this expression was derived with only two frequencies. We can use multiple frequencies to even expand our this unambiguous range even more. So thus so the limitation